Section 10.1, Integer Exponents. So let's go ahead and look at an example that will lead us to a negative exponent and then see how to deal with that. So they're asking us to simplify y to the third over y to the seventh. So one way I could attempt to deal with that is to use the rule that says if you have a division where the bases are the same, then you subtract the bottom exponent from the top exponent. So that would be y to the 3 minus 7. And if I do that, I get y raised to the negative 4, and I think that leads to the natural question, what does that mean? Y to the third means that we have a multiplication where there are 3 y's, but how can you have a multiplication where there's negative 4 y's? It's a confusing idea. So let me look at y to the third over y to the seventh and simplify that a different way. I could say that on the top I have y to the third, and in the denominator I have y to the third times y to the fourth. Notice that would still be the 7 y's just from here. I'm just splitting it up. And then at that point I could say this y to the third cancels that y to the third. So then what's left over? Well, in the denominator there's a y to the fourth. In the numerator everything's canceled, but when that's the case there's still a 1. So notice both times I started with y to the third over y to the seventh. One time I got y to the negative 4. The other time I did the work a different way and I got 1 over y to the fourth. If both of those methods are valid, then what that would imply is that both of these answers must be the same. So what does y to the negative fourth mean? Apparently it means the same thing as 1 over y to the fourth. So that's going to be our rule. Let's look at that as a definition. For negative integer exponents, if n is a counting number and b is not 0, then b to the negative n is 1 over b to the n. So that's just making the statement right here. If we have something raised to a negative power, we can get rid of that negative by doing the reciprocal, 1 over that base, and now the power is positive. So in words, define b to the negative n, take its reciprocal, and then you change the sign of the exponent. So essentially, how do we deal with negative exponents? We get rid of them. How do we get rid of them? By taking a reciprocal, because that changes the sign of our exponent. And then there will be times where we actually start off with the negative exponent in the denominator, but if we follow these words, we could still get rid of the negative by taking the reciprocal. And when you take the reciprocal, that brings the negative exponent up from the denominator to the numerator. So same words, in words to find 1 over b to the negative n, find its reciprocal, and then change its sign. Notice that's the exact same words both times. So if it's in the top, because you could think of this as b to the negative 1 over 1, then to get rid of the negative sign you move it to the denominator. If it's already in the denominator, think of this as over 1, then you move it up to the numerator. So let's look at a few examples of that. So if we have x to the negative 2, we want to take the reciprocal, make that 1 over x squared, and that changes the sign and the negative exponent is gone. If we're starting out with that negative exponent in the denominator, we bring that up to the numerator. That changes the sign of the exponent. We get y to the positive 5, and the negative exponent is gone. So those are the two basic examples of how this works. If you just have a regular negative exponent in the numerator or all by itself, you move it to 1 over, push it into the denominator. If it's already in the denominator, you get rid of that negative by bringing it up to the numerator. Alright, let's look at one where we have a few different factors combined together and see how we would deal with that. So I'm going to show it to you in kind of a long way and then a quicker way. So I'm going to take that 4 over negative 6 and just break that off to the side as negative 4 6. And then all the other factors I'm going to put by themselves. So b to the negative 9 is in the numerator, so I'm going to write that over 1. C to the fourth is in the denominator, so I'm going to write that as 1 over c to the fourth. And d to the negative 1, that's in the denominator, so I'm going to write that as 1 over d to the negative 1. And if you were to multiply across here, you'd get right back to where you started. And I'm going to start doing some simplifying now. The 4 and 6 have a common factor of 2, so I'll cancel that, and that'll reduce that to 2/3. And then I want to get rid of these other negative exponents. So let's see, let's start copying what we have. We have the negative sign and the 2/3. And then this b to the negative 9, I'm going to use this rule right here and make that 1 over b to the 9th, doing the reciprocal. And then this one is already a positive exponent, so I'm not going to flip that one. In fact, if I push that up to the numerator, its exponent would become negative, which I don't want, so I'm going to leave it alone. But here I have a negative exponent, so I'm going to move that one up top, and that'll change its exponent to positive. Notice, by the way, I did not move the negative 6 up to make it positive. If a number is negative, it's negative. If an exponent is negative, you can change that by doing reciprocals, but not a number itself, not a coefficient. Alright, if you look at what I have here, there's no negative exponents. So I could just multiply this out, and let's see what that would give. In the numerator, I'll put the negative, so I'd have negative 2 times 1 times 1 times d, so negative 2d. And in the denominator, 3 times 1 is 3, and then we have b to the 9th and c to the 4th. And that would be the answer to this question. I would just argue I got there a little slower than I needed to. So let me go ahead and show you again the same problem, but a little trick that I would use. If, in fact, we can even just almost look at it from the beginning to the end and see the difference. The negative exponent b to the 9th ended up in the bottom. It moved from the numerator to the denominator. The c to the 4th, which was already a positive exponent, stayed in the denominator where it started. D to the negative 1 moved up to the numerator from the denominator. So you could argue that the way I simplified the negative exponents in this more complicated scenario was I took the one that had a negative exponent in the denominator and I moved it up to the numerator. And I took the one piece that had a negative exponent in the numerator and I moved that down to the denominator. And the negative 4, the negative 6, and the c to the 4th had positive exponents, so they just stayed put. So if I was doing that, I would have just left the 4 and the 6 and the c to the 4th right where they started. The b to the negative 9th in the numerator, I would move down to the denominator. And then the d to the negative 1 in the denominator goes up to the numerator. And if you look at it basically in that one step, I've gotten rid of all the negatives. I would just need to reduce the 4 and the 6 still. And the 2 goes into there twice, into there 3 times. Multiply that out. And we're back to that same answer that we had a minute ago. So I wouldn't normally do it this way. This allows us to use the official rules, but if you look at it, the shortcut would be if everything's multiplication in the numerator and denominator and you have any negative exponents, you can get rid of those negatives by moving them across the fraction bar. Negative exponents in the numerator move down, the ones that are in the denominator already move up. Alright, continuing on to page 2, we're just going to do some more examples of simplifying when negative exponents are involved. And what I want to show you here on this page is that all of the properties that we learned for positive exponents can still be applied to negative exponents. So if you have two bases that are the same and you're multiplying, our rule before was to add exponents and leave the base alone. And you can still do that. So since both of these have a base 4, when I multiply, I keep a base of 4. And I just take the first exponent, 2003, and I add the negative exponent of 2000. And since that's plus a negative, it really just turns into subtraction. And 2003 minus 2000 would just be third power. And so we get 4 to the third, and that's 64. And just a couple things here I want to show you with the calculator. One of them is just kind of a quick check on that last piece. This is our, let me move this up just a little bit. This is our exponent key right here. So I can do 4 raised to the third and get 64 and see that that's right. But I want to show you that we actually had to use those exponent rules, because maybe you would have been tempted, I'll just put the whole thing in the calculator, right? If you try that and you do 4 raised to the 2003 and you press enter, you get this error overflow. And that's because that number, 4 to the 2003, is too big of a number for your calculator to handle. So you actually have to know how to use those sign rules or you're going to get stuck on this one. Alright, let's go ahead and look at another one. So on this one, we have some numbers and letters in each one, and you might remember from the previous sections with the positive exponents that we said multiply numbers with numbers and then like letters with like letters. So I'm going to follow that strategy right here and say negative 3 times that negative, which I'll think of as negative 1, would be a positive 3. B to the negative 2 times b to the 9th, that would be b to the negative 2 plus 9. When the bases are the same, you add the exponents. And then do that again with the c's. C to the negative 6 plus negative 1. I'll just write that as a minus 1. And now I want to simplify each of these. But it's the same rule as before, numbers with numbers and like letters with like letters by adding their exponents. And so let's see how that works out. The 3 is already done. Negative 2 plus 9 would be b to the 7th power. And the two negatives here would make this c to the negative 7. And because that's a negative exponent, that's not considered simplified. And so what I would do is put this whole thing over 1. And then to get rid of a piece that has a negative exponent, I want to move it across the fraction bar, so that's going to move down. And when I move that down, it's going to change its exponent from negative to positive. So the 3 has an exponent of positive 1, so it stays put. The b has an exponent of positive 7, so it stays put. But the c has an exponent that's negative, so I move that down to the denominator, and that changes the sign of that to positive. And then that one is simplified. Alright, let's try another one. So here, I'm going to go ahead and think about the exponent rules and say this is 2 to the 5 minus 2. When you're dividing, you can subtract exponents. And b to the negative 7 minus 2. I'm subtracting because it's division, and then there's another negative that was already on the exponent, so you got to be careful there. You do get two negatives. And then that's 2 to the 3rd. And let's see, that would be b to the negative 7 plus 2, or 2 to the 3rd times b to the negative 5. So a couple reasons this isn't simplified yet. One of them is the negative exponent, so I'm going to put this over 1. And I'm going to take this piece with the in the numerator with the negative exponent, move it down to the denominator. And the other reason this isn't considered simplified is the 2 to the 3rd can be worked out. So 2 raised to the 3rd power would just be 8. And then that b to the negative 5, we said we're going to move that down to the denominator, and it would become a positive 5. So that would be our answer. One of the things that you might notice on these, like if you start working on the problem before you see my solution, you might have done it a different way. With these exponent problems, there usually are many different paths that are all valid and lead to the same answer. So if you ever do one of these and use a different approach and you still end up with the same answer, odds are good that you're taking a valid approach. If you're nervous about it, you can check it with me later. But it's very common for people to take different paths here and still make it. Alright, let's look at another one, still continuing to use these exponent rules. One of the rules we had with our positive exponents that still applies is if you have a product raised to a power, you distribute that power to each piece. So I would take the b to the 4th and raise it to the negative 5th. And remember, if you have a power to a power, you multiply. So that becomes b to the 4 times negative 5, which would be b to the negative 20. And then I do the same thing with the c. C to the negative 7th raised to the negative 5th is a power to a power, so I multiply. And negative 7 times negative 5 is positive 35. It's always good when we get positive exponents because those are considered to be simplified, but the b to the negative 20 is not, so I'm going to put this over 1, and I'm going to move that across the fraction bar to change the sign of its exponent. So in the numerator, I'll still have that c to the 35, but the b to the negative 20 will move to the denominator, and that move changes the sign of its exponent to a positive. And I've mentioned this before, but it sometimes could be tempting to maybe cancel a 5 right here with the 35 and the 20, but those are not factors of the numerator. All we have in the numerator are a bunch of c's. There's no 35. There's 35 c's, but there's no number 35. And in the denominator, there's no number 20. There's 20 copies of the b, and you can't cancel a c with a b, so they have nothing in common. Exponents don't get canceled, not when they're the same base. Or when they're different bases. If it's the same base, you can sort of cancel them, but that's through subtraction, not division. Alright, let's move to the last one on this page. This one's looking a little bit messier. So I think the first thing I would do is try and get rid of all the negative exponents. So the d to the negative 7 I would move down. The d to the negative 2 I would move up. And let's see, we have a b to the negative 6, so that's going to get moved up. And it looks like that would be it for negative exponents. So let's see, on the numerator I had the 18, I'll keep that. I have b to the 5th, that's a positive exponent, I'll keep that. C to the 3rd, positive exponent, it stays. That d to the negative 7 I'm going to move down. So let's see, that negative 24 is in the denominator, and that c to the 3rd was in the denominator, and then the remaining three things are all on the move. So if you look at the 5 that I have copied so far, they're the ones that already had positive exponents. Remember, 18 and 24 have exponents of 1, which is positive. So that b to the negative 6 right there, is going to move up, change its sign. That d to the negative 2 is going to move up, changes its sign. That d to the negative 7 is going to move down. So all the negative exponents are gone at this point, so I'm going to just start simplifying. Some of the things I see right away, this c to the third could cancel that c to the third. Could have even done that at the original if I had noticed it a little sooner. Both of these numbers are divisible by 6. 6 goes into 18 3 times, and it goes into negative 24 negative 4 times. And then some other stuff I could cancel. These two d's, cancel 2 of those, and there'd still be 5 left over. And the 5 left over in the denominator because that's where there were more d's to begin with. And that just about does it. So let's see, we have the 3, and then we have a b to the 5th and a b to the 6th. So those are the same base, and I can multiply them together by adding exponents, so that would be b to the 11. And that's it for the numerator. In the denominator I have this negative 4, and all that's left out of the other cancellation I did is the d to the 5th. So that would be the answer there. I'm going to go ahead and box that. Maybe a little strange to leave the negative in the denominator, so you could move that up to the top if you want or out front. It is technically correct in the bottom, but usually we'd prefer it out front or in the numerator. So any of those 3 spots is okay. So I'll go ahead and leave it there. Alright, continuing on to page 3, let's go ahead and look at an example that involves negative exponents. A person plays an electric guitar outside, and the sound level, f of d, in decibels, at a distance d yards from the amplifier, is described by the equation f of d equals 5,760 times d to the negative 2. So simplify the right-hand side of the equation. So I'm going to just start off by copying the equation down. F of d equals 5,760 times d to the negative 2. Now when I wrote that just now I put the dot for times, which isn't necessary, but one of the things it does kind of show us when we do that is that these are 2 separate factors. 5,760 is one factor, d to the negative 2 is the other. And what's important to realize about that is this exponent of negative 2 is just on the d. It's not on the 5,760. That number has its own exponent. I don't see one, but that means it has an exponent of positive 1. And what's important to realize there is that means when we get rid of that negative exponent, we're only going to move the d to the denominator and make that a d squared. We're not going to move the 5,760 down because its exponent was 1, which was positive, so that can just stay put. So that would be considered the simplified version of the function because it no longer has a negative exponent. And then they want us to find f of 8 and think about what that means in the situation. So first let's just find it. So f of 8 means that we're going to plug 8 in place of d. So we'd get 5,760 over, instead of d squared, it would be 8 squared. So that's 5,760 divided by 64 if I do the squaring on the 8. And then we just need to divide to finish that off. So 5,760 divided by 64, that goes in 90 times. And then to help us think about what this means, we want to think about the units. So first let me put units here. 90 what? Well, that's a value of f, and f is measured in decibels, so that would be 90 decibels. And then to think a little bit more about that, what that means, how did I get that? I plugged in an 8, but 8 what? Well, 8 went in for d, so 8 was a value of d, and d was the number of yards we were from the amplifier, so that represented 8 yards. So then I just want to put that into words and say, if we're a distance of 8 yards away from the amplifier, we hear the sound at a level of 90 decibels. So let's write that out. So at a distance of 8 yards from the amplifier, the sound level is 90 decibels. So I think that the key when you're trying to interpret one of these or say what it means in the situation is to think about the units. So when you get this value of 90, that was a value for F. So go up here and look, what are the units of F? Decibels. The number we put in, 8, was a replacement for D, so what were the units of D? Yards. And once I realize that it's 8 yards and 90 decibels, I can start putting it together into a sentence. Alright, continuing on, I want to go ahead and show you another application of negative exponents, and that is that it comes up in something called scientific notation. So let's look at that definition. A number is written in scientific notation if it has the form n times 10 to the k, where k is an integer, and either n is in between negative 10 and negative 1, or n is in between 1 and 10. So this number right here is in scientific notation because the number out front, which would be like the n, is 8.31, and that's in between 1 and 10. And this says the same thing, it just means it could be a negative number also, but basically we want the size of this to be somewhere between 1 and 10. And then it's written as times 10 to some power. So what happens when you multiply by 10? It just moves the decimal over once. So what happens if you multiply by 10 6 times? It's going to move the decimal to the right 6 places. So if I work this out and think, what does this number really mean? And that is our directions here. Write each of the numbers in standard decimal form. Then I take that 8.31 and I move its decimal to the right 6 places, because I multiply by 10 once, it moves. I multiply by 10 again, it moves. And I do that 3, 4, 5, 6 times. So the first couple times I multiply, it just moves it past the 3 and the 1. After that, what you need are placeholders of 0 that the decimal is moving after, or moving past. And so our decimal is no longer over here, now it's at the end, which means that we're now looking at the number, let's see, we've got 8, 3, 1, and 1, 2, 3, 4 zeros. Throw our commas in there to help us visualize that. Looks like that number is 8,310,000 and no ones or hundreds. Let's go ahead and look at another one. First of all, why would this be considered scientific notation? The times 10 to an integer fits the times 10 to the k piece, and the number out front, 6.488, is a number in between 1 and 10. So this would be considered scientific notation. And so to think about what does this mean, there's just a little bit like of a guess, I could say, where if multiplying by 10 to the positive 6 means move the exponent to or the decimal place to the right, probably if the exponent is negative, I would move the decimal to the left. And that does turn out to be the case, but I want to show you why using what we just learned about negative exponents. If you think of this as over 1, then this becomes 6.488, and then we could say we want to get rid of the negative exponent, and that would move that down to the denominator where it would become positive. So now when you have times 10 to the 6, you're multiplying by 10, and that's why you move the decimal to the right. The number's going to get bigger. But if you have times 10 to the negative 5, that's really the same as dividing by 10 5 times. And every time you divide by 10, it's going to move the decimal to the left. The first move would go past the 6. The next 4 decimal moves to give us our total of 5 would create zeros. So this would be 0.1234, and then in the 5th decimal place will be that 6, and then 488. It turns out this is not a coincidence. Whenever you have one of these that's negative, that lead number always ends up being in that decimal spot. So when I have a times 10 to the negative 5, that lead number of 6 ends up in the 1, 2, 3, 4, 5th decimal spot. So technically what's happening is the decimal's moving from here 1, 2, 3, 4, 5 spots to the left, but that will always have the effect of putting that lead number in that decimal place. So what I try to remember here is that if you have a positive exponent, you're going to get a big number, and the exponent tells you how many places to move your decimal to get that big number. If you have a negative exponent, that means you're going to be dividing, and that means this is going to end up being a really small number, and the exponent tells you how many places to move the decimal to the left to create that small number. Alright, so here's a summary of what we just saw in those last two examples. Let me go ahead and read it to you and then give you kind of my take on it as well. So if you're converting from scientific notation to standard decimal notation, the book says that to write the scientific notation for n times 10 to the k in standard notation, we're going to move the decimal point of the number n as follows. If k is positive, then we're multiplying by n, multiplying n by 10 k times, and therefore we move the decimal point k places to the right. And if k is negative, then we divide n by 10 k times, and therefore we move the decimal point k places to the left. I think that rule is pretty good. I would just caution you against against memorizing this only. So I think if you said if k is positive, I'm going to move to the right, and if k is negative, my decimal is going to move to the left. I think that's really easy to get mixed up. So I think the middle part is very important. If k is positive, then you're multiplying by 10k times, and therefore it makes sense to move it to the right, because that's what creates a bigger number. If k is a negative exponent, you need to remember this part. That means that you're actually dividing n by 10k times, and therefore it makes sense to move the decimal to the left, because every time you divide by 10, a number gets smaller, and moving the decimal to the left makes that number smaller at the same time. Alright, let's go ahead and look at this from the other point of view real quick, which is, what if we have a number in standard notation and they ask us to put it into scientific notation? So let me pull in that previous page and that definition for you. So it says for a number to be in scientific notation, you have to have the lead part be in between 1 and 10. So if you want to take 280,000 and put it in scientific notation, you have to move the decimal from right here at the end to a place where the number would now be in between 1 and 10. And so if I put that decimal in between the 2 and the 8, then now we have a number that's 2.8, and 2.8 is in between 1 and 10. And then we would multiply that times 10 to some power, and the power would be equal to the number of places we moved the decimal, which was 1, 2, 3, 4, 5 spots. So it's either going to be a positive 5 or a negative 5, and what I would encourage you to remember is that numbers that are big have positive exponents in scientific notation, and numbers that are small, like this one, have a negative exponent. So we usually don't write all those zeros, so I'm just going to change this a little bit and say it's 2.8 times 10 to the 5th. Alright, and then let's look at another one. On this one, we want to do the same thing. Move the decimal so that after we're done moving it, this number is between 1 and 10, and 2.3 is in between 1 and 10. And then think about, alright, how many places did I move the decimal to make that happen? 1, 2, 3, 4, 5. So I'm going to go times 10 to some kind of power of 5. But if your number is going to be a small number, that's when you need the negative exponent. And if you're ever not sure if you put it in right, take it out. Right? Take 2.8, multiply by 10 5 times. That gets you back to this big number. Take 2.3, divide it by 10 5 times because of the negative exponent. That'll take you back to this small number. So if you're ever unsure if you put the sign on there right, just work it back out the other direction and see if you get back to where you started. But the thing that I remember to make this quick for myself is big numbers have positive exponents in scientific notation, and small numbers have negative exponents in scientific notation. Alright, let's go ahead and look at one final example. The number of different 8-character passwords that can be made from 26 letters and 10 numerals is approximately 2.8 trillion. Write that in scientific notation. So first let me just do the translation of the number, and then we'll deal with the writing it in scientific notation. So 2.8 trillion is 2.8 times, I've done this with you a few other times, where if it said thousands, I go times 1,000. If it says a million, I put times a million. Well, this one says a trillion, so I'm going to multiply by a trillion. That would be 1,000. 3 more zeros, that would be a million. 3 more, that would be a billion. And 3 more, that would be a trillion. So to switch this into just regular numbers, I'm going to change the word trillion for times the number a trillion. But thinking about scientific notation, 2.8, that's actually where we want the decimal place, because that number is between 1 and 10. And then we want times 10 to some power. Any number that starts with a 1 and is followed by all zeros is 10 to a power, and you can tell what power it is by counting the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 2.8 times 10 to the 12th. And this is now in scientific notation. because this number right here is between 1 and 10, and then we have times 10 to some power. And again, you can verify on your calculator. I think this will fit on the screen. Maybe not, that might be too long. But 10 to the 12th is a trillion. And again, it's the number of zeros matches the power on 10, and we have that 1 there already. So if it was a different number, it would complicate things a little. Alright, that ends that problem, but then there's this part in parentheses. How did they get that value? So let's say we were trying to make a password. We were going to type 8 characters, and they told us every character can be either a number or a letter. Then each time you go to, well, let's just kind of write it out as a fill in the blank. You have 1, 2, 3, 4, 5, 6, 7, 8 different choices that you're going to make. So, pick a number or a letter here. So how many choices do you have in that first spot? You have 26 letters or 10 numbers, 0 through 9. So that really gives you 36 choices in that spot. And when you move and think about the second character of your password, that has 36 choices too. And that's true about every one of those spots. You have 36 different choices for how it's going to turn out. And we'll talk about this later on in the course, but it turns out that when you have consecutive choices like this, and you want to think about how many combinations does that make overall, you end up multiplying that together. So for every character, you have 36 choices. And 36, let me brighten that up a little bit, 36 raised to the 1, 2, 3, 4, 5, 6, 7, 8 copies of that gives you 2.821109907E12. That E12 is the calculator's way of saying times 10 to the 12th. And so notice there's our 2.8. They've rounded it off apparently here, but it's 2.8 times 10 raised to the 12th. So that's where they got that from. 36 choices for each slot, and you have 8 slots that you're trying to choose either a number or letter for. All right.